Welcome to Yatim Khana and Madrasa Anjuman Khairul Islam's Pune College of Art, Science and Commerce Camp Pune 1. Myself, Dr. Arif Tamboli, working as Associate Professor in the Department of Electronic Science. Dear students, this is the third lecture in the series of ASTABLE multivibrator using IC555. In today's lecture, we are going to study how to derive the formula for the frequency at the output of IC555. So let us proceed for that formula for deriving the equation at the output of IC555. So here you can see this is the derivation for the formula of frequency at the output of IC555. So this is there. So this is our title, derivation for the formula of frequency at the output of IC555. So we know that capacitor, which is externally connected at the circuit diagram of IC555 as a stable multivibrator, that capacitor gets charged exponentially to the value of 2/3 VCC through the resistor RA and RB. So this already we have studied in the previous lectures. Secondly, we also know that the said capacitor, which is externally connected, gets discharged exponentially. So the charging as well as discharging of capacitor is exponential. As I told you that this exponential nature is because our capacitor C charges with the help of a current which is not constant. So that is the reason why it is exponentially charging. If the current source to charge the capacitor is a constant current source, in that case only the charging of capacitor will be linear. So this you remember, in future sometime we'll come across that topic. So the discharging of capacitor also takes exponentially and not linear. And this capacitor discharges to the value of 1/3 of VCC. Number one. Number two, the discharging of capacitor takes place only through RB. So this is the important thing. So charging of capacitor takes place through RA as well as RB, and discharging of capacitor takes place through RB only. So before proceeding to the derivation of frequency at the output of IC555, I will just explain you once again how long time logic 1 remains at the output of IC555 and how long time logic 0 remains at the output of IC555. So in short, we'll proceed for that. So the title will be like this: time period for the discharge of capacitor, that is time period for logic 0 level, LVL, that is called low voltage level. So all of you know that in the previous lecture we have connected the circuit for IC555 as a stable multivibrator, and when we connected the circuit and when we applied the power supply, we know that externally connected capacitor C starts charging through RA and RB. So the moment as soon as we connected the power supply, at that time t is equal to 0, we have considered that our capacitor was initially discharged. And therefore, because of that consideration, the output of the flip-flop Q becomes logic 1. And therefore, whenever IC555 is used as a stable multivibrator and power supply is turned on, at the output of the square wave, you will observe high voltage level. And when high voltage level is observed at the output of IC555, means pin number 3 is at HVL and pin number 3 is the output terminal of IC555, which is taken from output Q of the flip-flop. Therefore, when output Q of the flip-flop is in HVL, no doubt Q bar is in LVL. And because of that Q bar is in LVL initially, this Q bar is applied to the base of transistor. You will recall, you will get everything. This Q bar is applied to the base of transistor and transistor behaves as open switch and therefore charging action starts. Now consider that our capacitor is started charging. It will cross 1 volt, it will cross 2 volt, it will cross 3 volt, it will cross 4 volt, and like that when it will cross the 5 volt level, you know that both the input becomes 0 0, but output will remain in previous state, that is 1 and 0. But when the capacitor starts charging above 5 volt, 6 volt, 7 volt, 8 volt, 9 volt, 10 volt, and when the capacitor goes above 10 volt, so let us say 10.1 volt over here. So this voltage across capacitor, that is plus and minus here, this voltage is becoming 10.1 volt. So this is pin number 2, this is pin number 6. Both pins are lower terminal of upper comparator as well as lower comparator. So pin number 6 is at 10.1 volt, pin number 2 is also at 10.1 volt because capacitor has just charged to the 2/3 of VCC. Under this condition, output of upper comparator will be logic 1 because voltage at pin number 6, that is positive terminal, is greater than voltage at negative terminal. Remember here I have written 10 volt because we have applied plus VCC as a 15 volt and this terminal is nothing but 2/3 VCC. We have removed the potential divider. We know that the voltage at this point is always 2/3 of the VCC. To avoid the complications, henceforth we are not going to draw three blocks, each of R1, R2 and R3, where 2/3 of the VCC and 1/3 of VCC will appear. So we'll simply write here 2/3 of VCC means 10 volt, 1/3 of VCC means 5 volt. So these voltages are fixed, 2/3 of VCC and 1/3 of VCC. So as long as now our VCC is 15 volt, this will be 10 volt, this will be 5 volt. So let us think now output of comparator is 1 and 0. Therefore, as soon as the output of comparator becomes 1 and 0, that is just capacitor start to the 2/3 of VCC or just above the 2/3 of VCC by few millivolt, the output of flip-flop will become 0, which was earlier logic 1. So S is 0, so Q is 0. And as soon as Q becomes 0, you know that Q bar is 1. Therefore, this Q bar is applied to the base of transistor. So 1 means logic 1, that is high voltage level. And this high voltage level is more than sufficient to forward bias the emitter to base junction. And transistor will force into conduction. It will behave as a closed switch. So the moment as soon as capacitor charges to the value of 2/3 VCC, the output changes and transistor behaves as a closed switch. Therefore, here charging action will stop now because the capacitor which is already charged to 2/3 of VCC will start discharging through RB. You see the red arrow. So how does the capacitor discharges? Capacitor discharges through RB. Why it discharges? Because this terminal is now short circuited through the closed switch to the ground. Means our capacitor is now short circuited with the help of RB. So this is the first action taking place. Secondly, as capacitor starts discharging, at the same time the power supply is continuously on. Therefore, the current flowing through the power supply will now select the least resistance path, that is short circuit path, and will go to the ground. So this is in this way here logic 0 will be there. Now we just wanted to say that how long time logic 0 remains there. So the moment as soon as the capacitor starts discharging, whatever we have considered earlier, that is the capacitor just crossed the level of 2/3 VCC, means just about 10 volt. So the moment as soon as capacitor start discharging, this voltage 10.1 volt will not remain 10.1 volt. It will go below 10.1 volt and it may become 9 volt, it may become 8 volt, it may become 7 volt, and like that. This voltage as soon as it goes below 10 volt, then what happens? Let us see. in the next picture, so you will understand that. So here in the next diagram, this is 10 volt, no doubt 2/3 of VCC. This is 5 volt, no doubt 1/3 of VCC. Now when the discharging of the capacitor starts, then this voltage, which was earlier written 10.1 volt, will not remain 10.1 volt. It will go below 10.1 volt, then 9 volt, then 8 volt, then 7 volt, then 6 volt, and then 5 volt. But the moment as soon as it goes below 10.1 volt, you know that this output will become 0. Very simple, because 10 volt, and when it is below 10 volt, say 9.9 volt. So when this is 9.9 volt and this is 10 volt, this voltage is higher, negative terminal. Therefore, this will go in 0. But again, remember, as I told you, when both inputs of the flip-flop are 0, 0, the output of the flip-flop will latch to the previous state. Means the output Q will continue to 0 because earlier it was 0. And in this way, even though this voltage at positive pin of the upper comparator as well as voltage at negative pin of the lower comparator goes below 10 volt, the output of upper comparator is 0. The output of lower comparator, no doubt it will be 0, and logic 0 will continue to remain. So here, from what value to what value capacitor get discharged? Capacitor started discharging from 2/3 of VCC and going down to 1/3 of VCC. So 1/3 of VCC is 5 volt. So now at this condition, when both inputs are same, output is again 0. But when capacitor discharges just below 1/3 of VCC, say 4.99 volt, when capacitor discharges just below 1/3 of VCC, that is 4.99 volt, till 5 volt, see, discharging action of capacitor is continued. Means till 1/3 of VCC, the discharging action of capacitor is continued because transistor is closed switch. So here logic 0 will remain there till the capacitor gets discharged from 2/3 VCC to 1/3 VCC. Now, as soon as this voltage across capacitor goes below 5 volt, that is 4.99 volt, the action will be somewhat like this. And you will understand now that this is plus VCC 15 volt, that is 10 volt, this is 5 volt. Now here I have considered 4.99 volt. The moment as soon as this becomes 4.99 volt, no doubt this terminal is also short circuited to this terminal. Therefore, voltage across capacitor simultaneously gets applied at pin number 2 and 6. So this also becomes 4.99 volt. So now what happens here? The lower comparators, lower terminal, that is minus terminal, negative terminal, becomes 4.99, and upper is fixed 5 volt 1/3 of VCC. So as soon as capacitor get discharged just below 1/3 VCC, output of lower comparator becomes 1. And as soon as the output of lower comparator becomes 1, set will become 1. Q is remaining 0 only. And this is what our previous condition, first condition, when we started in the beginning by turning on the power supply. So S is 1, therefore now Q will be 1. And in this way, the output of the flip-flop will again come back to the logic 1. So here what I have tried to explain you is how long time the logic 0 remains there. So the logic 0 will remain there till the capacitor gets discharged from 2/3 of VCC, means almost from 10 volt to the value of 1/3 of VCC, that is almost to the value of 1/3 of VCC, means in our example 5 volt. So this is the time duration for which at the output LVL remains, means logic 0 remains. And how long time logic 1 remains there, that already we have studied in the previous lecture, till the capacitor does not get charged from 0 volt to 2/3 of VCC. Till the capacitor does not get charged from 0 volt to 2/3 of VCC, at the output logic 1 will continue to remain there. And if you have understood this, then it is very simple. In the beginning, whatever we have considered like this. So here in the beginning, our switch was open and the output Q was 0. But in the beginning only, the capacitor starts charging from 0 to 2/3 VCC. And later on, the capacitor will start charging from 5 volt, that is 1/3 of VCC, to the 2/3 of VCC. So here in the diagram, it is very clear. Once again, you see, in the beginning only, capacitor will start from 0 volt to 2/3 of VCC and output will remain in logic 1. Then capacitor will discharge from 2/3 VCC to 1/3 VCC and output will remain in logic 0. Then again the capacitor will charge from 1/3 VCC to 2/3 VCC, means 5 volt to 10 volt. And in this way, from this explanation, you might have been understood that the total time period T of this square wave which is generated at the output of IC555 is a combination of HVL and LVL. So HVL means high voltage level, LVL means low voltage level. So time required for charging the capacitor from 0 to 2/3 VCC is called as T charge. And for that T charge, whatever time required to charge the capacitor from 0 to 2/3, that T charge is again entirely decided by you people, because when capacitor charges, capacitor is external, it charges through RA and RB. You can decide the value of RA, RB and C, and this T charge will be there. So HVL remains as long as capacitor charges from 0 to 2/3 VCC. So this is the T charge. Next, T discharge. T discharge is also decided by you because capacitor discharges through RB, and when you select the value of capacitor and value of RB according to your choice, you can decide whether the charging should be very slow or whether the charging should be very fast. So like that, T discharge is also decided by you, and logic 0 will remain there for the time unless and until the capacitor does not discharges from 2/3 of VCC to 1/3 of VCC. So if you understood this, then derivation for the frequency at the output of IC555 is very simple, and we'll proceed for that now. This square wave, if you observe on CRO, then on CRO you can calculate this time. That is very simple. So on CRO you can calculate this time from this positive edge to this positive edge, and this time period, suppose if you got 10 millisecond, if you got 20 microsecond, then you know this time which is in millisecond or microsecond. You can calculate the frequency by using the formula F is equal to 1 by T. But now today's our intention is not to calculate the frequency of the square wave generated at the output of IC555 by using CRO, but we want to calculate the frequency at the output of IC555 by using the formula. That formula also you know that F is equal to 1.44 divided by RA plus 2 times of RB into bracket and then C. So that formula, how it comes? Why there is 1.44? Why 2 times of RB? So that formula will derive and then we'll understand that very easily. So let us proceed for here. Now come to the topic, derivation for the formula of frequency at the output of IC555. Then again, as I told you, once again in short, we'll repeat that. We know that the capacitor charges to the value of 2/3 VCC, number 1. Number 2, it charges through RA and RB. We also know that the capacitor charges to the value of this capacitor discharges to the value of 1/3 VCC and it discharges through RB only. Now let us talk about the time required to charge, that is called T charge. So this T charge equation is written, and I will tell you the trick to remember this T charge equation. Don't mug the equation. So here T charge is equal to, we are calculating the time required to charge the capacitor. So capacitor, if it is very big, it will take long time to charge. Capacitor, if it is very small, it will take small time to charge. So capacitor value itself is a very important factor in deciding the time required to charge the capacitor. So capacitor C first of all comes here. Whether the capacitor is small or capacitor is big. If you take picofarad capacitor, picofarad means 10 raised to minus 12. it will get charged very fast. If you take the capacitor microfarad, it is get charged little bit slow. And if you take the farad, it will take long time to charge. So value of C is very important. So in T charge, first of all, C comes. Then you know very well, capacitor charges through RA and RB. So addition of RA and RB. So into bracket addition of RA and RB. Now here capacitor charges through and RA and RB, therefore RA plus RB. Bracket close. Now here why the log is there and to the base E. Base E means exponential. So here the log to the base E, because in our IC555 externally connected capacitor C charges exponentially. That's why this logarithmic factor comes, and that is to the base E, not to the base 10. So this is very important. Externally connected capacitor C gets exponentially charged. Therefore, there is a logarithmic term, and that base is E. Now into bracket. Into bracket, what is there? So into bracket, 2/3 VCC divided by 1/3 VCC. This you remember now why it is came. Because our capacitor voltage continuously changes from 2/3 VCC to 1/3 VCC. It will charge to 2/3 VCC, then it will discharge to 1/3 VCC, and then again it will charge to 2/3 VCC. So like that here, this ratio is always there, 2/3 VCC to 1/3 VCC. And this is very simple to remember. Time required to charge the capacitor, T charge, depends on value of capacitor itself, as it charges through RA and RB. Therefore, addition of these two into bracket, capacitor charges exponentially. Therefore, there is a log to the base E. To what value capacitor charges? To 2/3 of VCC. To what value capacitor discharges? To 1/3 of VCC. Therefore, ratio of 2/3 VCC to the 1/3 VCC comes into the bracket. And this is very simple, you can remember. Then what we'll do? We will go for simple mathematics. VCC will get cancel. 2/3 divided by 1/3 will come to the 2, and will convert log to the base E to the log to the base 10. So all of you know, when you convert the log to the base E to the log to the base 10, you have to multiply by 2.303. So the same equation will come here, 2.303, because here I have converted log to the base E to the log to the base 10. That's what is there. Otherwise, C will remain as it is. RA and RB are there, so there is no change. And now very simple, next step, T is equal to 2.303, C is there, into bracket RA plus RB is there, log to the base 10 of 2, you can calculate with the help of a calculator, you will get it 0.30. And in this way, this equation is very simple. Now just we'll go to the one step ahead, that is simple mathematics. T is equal to 2.303 into C into bracket RA plus RB into 0.30. Multiply this 0.30 to the 2.303. You will get T charge equal to 0.69 into C RA plus RB. This will be our equation number 1 for T charge. Similarly, let us go to the equation of T discharge. So time required to discharge the capacitor. T discharge. So now this time depends on what factor, let us see. As I told you, if the capacitor is very big and you have charged it to 2/3 of VCC, and thereafter if you are if you are decided to discharge it, as already very large or very big capacitor is there, so you will require large time to discharge it. That again depend on how you are discharging through a very small resistor or discharging through a very high value resistor. So two factors are very important, value of capacitor itself and RB, because RB is responsible to discharge the capacitor, because our capacitor C discharges through RB only. So here you see there is a C and there is RB. So these two factors are only there in discharging, value of capacitor C and value of resistor RB. If RB is in mega ohm, capacitor will discharge very slow because current passing in mega ohm resistor will be in microampere. If RB is in kilo ohm, current passing through that kilo ohm resistor will be in milliampere, and accordingly. Now again here log to the base E. Why log to the base E? Because again when our capacitor discharges, it discharges with the exponential nature. Therefore log to the base E. And into bracket 2/3 of VCC to the 1/3 VCC, because always the voltage of across capacitor changes from 2/3 VCC to 1/3 VCC. So this is remaining there, and it is very simple now. Here C as it is there, RB as it is there, log to the base E as it is there, 2/3 of VCC by 1/3 of VCC, VCC will get cancelled, and if you do this mathematical calculation, you will get log to the base E of 2. Let us go now, convert this log to the base e to the log to the base 10. So when you convert log to the base e to the log to the base 10, you multiply 2.303, C as it is, RB as it is, log to the base 2, log to the base 10 of 2. Now, this calculation you do it, you know very well, you will get T discharge is equal to 0.69 into C into RB. 0.69 into C into RB. So you got two equation. Equation number 1 for T charge and equation number 2 for T discharge. Now you know very well the total time required to charge, means the total time of the square wave is nothing but your T charge plus T discharge. So that equation you know, we know that T is equal to T charge plus T discharge. Therefore, let us write the equations for that. We know that total time T is equal to T charge and T discharge. For T charge, what was the equation? For T charge, the equation was 0.69 C into bracket RA plus RB, because our capacitor was charging through RA and RB. Bracket close, finish. Plus T discharge. What is the equation for T discharge? 0.69 C into RB only, because capacitor discharges through RB. So these two equations we have written as a T charge and as a T discharge. Very simple now. 0.69 and C. See here in this equation of T charge, this 0.69 and C is there. In this equation of T discharge, there is a 0.69 and C is here. So let us take 0.69 and C as a common. So into square bracket, what will be there? RA plus RB plus this RB. So it's simple mathematics. We have taken 0.69 C as a common and into bracket rest thing, RA plus RB plus RB. And it's very simple now, 2 times of RB here will come. So 0.69 into C into bracket RA plus 2 times of RB. And this is equation number 4. So this you got total time T. So this is the total time T. Now you know very well the equation for the frequency F is equal to 1 by T. So when F is equal to 1 by T, then we can write, yes, we can write F is equal to 1 by T, and whatever the formula for the T which we have derived, that is 0.69 into bracket RA plus 2 times of RB bracket close and C. Okay, this C you can take here also, or you can take here also, below, before the bracket or after the bracket, doesn't matter. So here like this, then F is equal to 1 divided by 0.69. Simple mathematics. You take a calculator, you will get 1 divided by 0.69 as a 1.44, and therefore the equation will come as F is equal to 1.44 divided by RA plus 2 times of RB bracket close C hertz. So you take all these value in basic unit, resistor in ohm, capacitor in farad, and simply you will get this frequency in hertz. And in this way, I hope you have understood that the derivation for the frequency of square wave at the output of IC555 used as a stable multivibrator. It is very simple. Now, after understanding all these things about IC555, I will ask you simple two questions, because this is very important as you have studied IC555 in detail, each and every block, charging of capacitor, discharging of capacitor, working of flip-flop, working of comparator, role of potential divider circuit, and transistor as a switch, means role of transistor to discharge the capacitor through RB. Pin number 7, that is collector of transistor, is a discharge pin, and everything. Now, after understanding all these things, let us conclude me. that by asking a simple questions. Okay, see the question. Does IC555 controls the charging time and discharging time of external capacitor? So I'll read the question again. Does IC555 controls the charging time, I have underlined, red underline, and discharging time of external capacitor? So external capacitor is C. Dear students, answer is no. Why? Because you know very well, externally connected capacitor C charges through RA and RB. How long time capacitor will take to charge to the two-third VCC is entirely decided by value of capacitor, value of RA, and value of RB. Therefore, IC555 does not controls the charging time and discharging time. So charging time and discharging time is controlled by you people. You select the value of RA, RB, and C. According to your choice, you decide whether the capacitor should get slowly charged or capacitor should get very fast charge. Similarly, you decide the value of RB. If RB is low, your capacitor will discharge fast, and if RB is of high value, capacitor will discharge slow. So answer is no. IC555 does not controls or decides the charging time and discharging time of capacitor C. It depends on the value of RA, RB, and C while charging, and it depends on value of RB and C while discharging. So like that the answer is there. Now next question. Does IC555 controls the charging and discharging of capacitor? So now see here. Once again I will read the question. Does IC555 controls the charging and discharging of capacitor? Here charging and discharging only. After charging word there is no time. After discharging word there is no time. Does IC controls the charging and discharging of capacitor? Answer is yes. Answer is yes. Because what is the reason? The reason is like that IC555 controls the charging of capacitor. Why it is said like this? Because the role of potential divider circuit is very important in this factor. The potential divider circuit is having two-third VCC and one-third VCC as a fixed voltages. Therefore, in case of IC555, the capacitor charges to two-third VCC only and capacitor discharges to one-third VCC only. See, IC555 controls the charging of capacitor. It charges only up to two-third VCC. That's why that is called control action. IC555 does not allow to charge the capacitor greater than two-thirds of VCC, that is equal to plus VCC. No, it controls the charging. And what is the controlling factor? Controlling factor is the potential divider circuit's two-thirds VCC. Therefore, that two-thirds VCC is only the magnitude of voltage to which the capacitor gets charged. And IC555 also controls the discharging of capacitor. Why it is said? Because it only discharges the capacitor to the value of one-third VCC and not below that. Therefore, here it is said that only controlling action is controlled, means capacitor charging two-third VCC and discharging one-third VCC is controlled by the IC555. So the answer to this question, does IC555 controls the charging and discharging, is yes. But if you say, does IC555 controls the charging time and discharging time, time is not controlled by the IC555. Charging time and discharging time is controlled by value of RA/RB during C during charging and like that discharging. So now last, here I will take only one example, and that example is for what? Calculate the frequency of square wave at the output of IC555 given RA 1 kilo ohm, RB 1 kilo ohm, C 1 microfarad. So the example is also very simple. Answer: F is equal to 1.44 divided by RA plus 2 times of RB into C hertz. So given value is 1.44 constant, 1 kilo ohm plus 2 times of Rb, again 1 kilo ohm, C is 1 microfarad, and like that you proceed, convert kilo ohm after that into a what? Ohm, and then finally you'll find out that when you convert the kilo ohm into ohm, microfarad into farad, basic units of resistor, basic unit of capacitor, and then value will be in hertz. Need not to write these things again. 1.44 divided by 3 into 10 raised to minus 6 and 10 raised to plus 6 will result as a 10 raised to minus 3. So 10 raised to minus 3 will go upside and this will become 10 raised to plus 3, and like this the frequency is F is equal to 480 hertz. So thank you for watching this last video in the series of IC555 as a stable multivibrator. So in 3 lectures, I have completed the entire application of IC555 as a stable multivibrator and derivation for IC555 as a stable multivibrator. So in this way, once again, I thanks you for watching the video. Now we'll proceed for in the next lecture for the next applications of the IC555. Thank you very much.